All right, good morning, folks. So just a little bit of housekeeping before we get started. I finally figured out what the problem was getting Lockdown Browser to install and work. Uh, it was very frustrating because all the tutorials kept saying, go to such and such page where you can turn on these settings. And I'm like, that page doesn't exist. But it's because when you click on the thing, there's a landing page and a little tiny link that says continue on. And I wasn't kidding the continue on thing. I didn't realize that it opened up an entire new set of settings that I could use. So anyhow, got that figured out after much frustration. And so your exam went up way later than I intended, but it's up now. And I went ahead and gave you guys until midnight on Wednesday to get it done, just because people's schedules are different, and I wanted to make sure that everyone had ample time to find a moment, while at the same time not keeping it open for so long that I run into exam security issues. So hopefully this is a good happy medium between the two, and we can get this taken care of. So just to make sure that everyone is clear, because there were some issues, let me screen share real quick. So if you go to the Canvas site, here's the home page, and it's the list of modules. And of course, here is the set of class videos. Several of you guys have commented that you had a hard time finding class videos, especially the older ones. And the reason why is because you weren't looking here, right? This is where all the class videos migrate to after they come off of the cloud recordings. If you go to the Zoom tab pictured here, many of you guys have probably already done this, where you go here to cloud recordings, and what's going to happen is the most recent ones are here. These are the ones that haven't been transferred. I think some of these have been transferred. I haven't deleted them yet, but I do delete them periodically just to make sure that I limit the amount of space I keep in the Zoom cloud. So once I delete them from this location here, they will all eventually be moved into this class videos section. However, if you look below the class videos module, you will find, oh, look, an exam one module. And in that exam module, you've got to complete all the items. It's going to require that you do them in order, just so you know. So the first thing you'll do is you will click on this lockdown browser check. And when you click on there, it should give you a prompt to download and install the lockdown browser if you haven't done so already. So if you're worried about not knowing where to go to get that download, this is where it is. It'll be there. So you'll download that. It will run you through a little 2-question quiz that doesn't count toward your grade at all. It's just kind of there to make sure that you can answer quiz questions. Hopefully you know both my name and the greatest superhero of all time, because that'll get you 100. And it'll run you through all of the camera checks, the audio checks, just to make sure that you see how the process ought to work. So once you've submitted that and gotten the 20 points for that, again, it doesn't count toward your grade, but it does count toward unlocking the rest of the stuff. Then it'll open up your exam one. And again, if you have any kind of issues doing this first assignment, please don't click on exam one until you're sure that things are going to work. That's why the lockdown browser check exists, is to make sure that there are no technical issues on an assignment that doesn't count before you open up the one attempt on the assignment that does count. So you'll open up exam one. It's short. I went ahead and just didn't use any of the multiple choice conceptual type questions that I would normally do for an exam. And so it's just the 4 straight up problems for 25 points each. And you'll turn those in. Once you have submitted those, you have 2 hours for that exam. Hopefully it won't take you that long. But within about 10 to 15 minutes of submitting that exam, you'll click here on the submit your work thing, and that's where you will upload a scan of some kind or a photo of your work. Make sure your work is legible. Make sure that it's well labeled so I don't have to guess what I'm looking at. So You know, if you're doing question one, make sure question one appears in big numbers. Ideally, make sure they're in order. That'd be great. The easier it is for me to navigate it while I grade is the better for me and for you. But you'll submit that. If there's any sort of reason why you can't submit that work within about 10 or 15 minutes of finishing the exam, I need to know about it immediately. I had to reject at least one person's work on the final exam this last spring because they took the exam toward the end of the window. The stuff closed, and then I got an email 15 hours later saying that, you know, oh, I can't make this work. You know, our campus was giving me problems. So here's the email of my work. But the problem was the first I heard of it was that email 15 hours later. That's not acceptable, right? So that Google Voice number in the syllabus, that's the kind of time where maybe it's justified to make that call. The other thing that I will point out is make sure you budget yourself enough time. If you wait until 11 o'clock on Wednesday to start the exam, it's going to cut you off at the due date. And unlike my homeworks where you can turn stuff in late, the exam can't be done late. It will lock after the time is allotted. So make sure you give yourself enough time to do all of that stuff. Otherwise, I can't help you. All right. And yeah, Tamisha, I saw your email. We'll talk about what we're going to do for you. I know you've got some technical issues, but we're going to work around those. But I'm aware. So, anywho, so that's where we're at. If there's any questions about that exam, please let me know. Okay, let's get to work on doing some physics.
What if we don't have a working camera?
You're gonna have to have a workaround. I'll talk to you about that after class. But we're gonna have to do something for exam security. But yeah, Tamisha's in the same boat as you, actually. So we'll figure that out. Give me. How about this? Try making an office hour appointment, and we'll talk through that. Now, you don't have a camera even like on your iPhone or something?
I have it on my iPhone, but on my laptop, it doesn't work. And the laptop that actually can, because I have two laptops. The one that is broken has lockdown browser. The screen doesn't work, and it crashes a lot. And
let's not do that.
Yeah. But the other one, it won't let me. It won't allow me to use lockdown browser. Like I tried everything, and I can't even do it. Like I even went on a website and through customer service, and nothing happened.
Curious. So what has been done? There's some workarounds for that, but I'm going to have to work through logistics before, and it's going to be different for every student because I have to work with what you've got available. So let's think through that. I have some ideas, but let's table that discussion for not now. All right. So at this point, we've got chapter 21 pretty much in the bag. We've finished all the stuff with DC circuits. So hopefully you guys are up to speed on that. The next place we're going to go is we're going to, again, sort of switch gears, and we're going to introduce a phenomena that is related to but distinct from the electric fields that we learned back in chapter 18, and that's going to be the magnetic field. Now, here's an insight that has come out of physics education research that kind of sums up the issue that we're going to have coming into this chapter. So what people have found is that if you take a group of students and you teach them about electric fields and you test them on electric fields and get them to score within the range of proficiency, and then you go on and you teach those students about magnetic fields, when you go back and you test those students again over their knowledge of electric fields, they do worse. It's like learning about magnetic fields causes students to do worse on electric fields. And the going thinking is that it's because these two things are similar in a few ways, but with some very striking differences. And what happens is when students learn about magnetic fields, they get confused about what's what. And that causes them to sort of unlearn things that they had previously done pretty well on. So that's going to be the thing we're going to be faced with, is we're going to have to introduce this new kind of field. And it's going to be different enough that it might even cause problems with stuff you've already hopefully mastered. So usually when I introduce this topic, what I'll do is I'll kind of go point by point and try to highlight like what the distinctions are between these two things, so that hopefully it keeps it fresh in your mind where this stuff is different and how to approach it differently. So we're going to do a little bit of sort of review by way of this. So let's switch my camera. Messy table. There we go. So let's start with what we know about electric fields. Not fields, Fields. And then right down the middle, we'll be able to contrast that with magnetic fields. So the first thing that we want to talk about is when we learned about electric fields, we learned that electric fields were caused by charges. Now, it's caused by those charges simply by virtue of the fact that those charges exist. Now, in chapter 23, we're going to learn some ways to create electric fields besides that. But again, for the time being, charges that simply exist create electric fields everywhere. If I was holding in my hand a little positive point charge, then what would happen is that positive point charge creates a disturbance all around itself. And that disturbance, the electric field, is created all throughout space simply because that positive point charge exists. Now, by comparison, magnetic fields are also created by charges. However, they're created by charges that move. So what's going to happen is if I've got one positive point charge over here and another positive point charge over here, what's going to happen is this positive point charge is going to create an electric field everywhere. The mere fact that that charge exists means it's creating an electric field. And because it's creating an electric field, there's going to be a force acting on the other point charge because of the electric field of the first point charge. So the mere fact that the charge exists means it will create an electric field. Magnetic fields are different. If I have two positive point charges and I take this positive point charge and I move it around, as I'm moving it around, it is generating a magnetic field everywhere around itself. In addition to its electric field, it is also creating a magnetic field. Right? But the minute I stop it, that magnetic field is going to go away. The electric field will still be there. So magnetic fields only get created when charges are moving. Now, we know that electric fields create forces on other charges. And from the definition of electric field, right? The definition of the electric field is E equals the force you'd feel over Q. If I just rewrite that a little bit, F equals Q times E, where E and F are both vectors. That's the Coulomb force law. Now, we learned the Coulomb force law for point charges. That's the K, Q1, Q2 over R squared. But this is true in general, even for non-point charges. So that's what we learned, that electric fields create forces on charges to the tune of whatever the charge feeling the force is times the electric field created by the other charge. All right, that's the Coulomb force law. There's going to be a force law for magnetic fields as well. However, the Coulomb force law is going to have an equivalent, and that equivalent is called the Lorentz force law. And because the Lorentz force law looks the way it does, it's going to create forces only on moving charges. So the force law for a magnetic field is F equals Q V cross B. This is called the Lorentz force law.
Don't start. Don't start.
So if I've got two charges, 1 and 2, and this charge over here starts to move, it's going to create a magnetic field everywhere, including at the location of the other charge. However, even though it's creating a magnetic field, the other charge won't feel any force on it at all until I try to move that charge as well. Now, once I start to move that second charge, it's going to feel a second force in addition to the Coulomb repulsion from the electric field that it wasn't expecting, right? That's the force from the magnetic field. And the force law given is the Lorentz force law. In the Lorentz force law, F is obviously the force that is exerted. That's pretty straightforward. Q is obviously the charge feeling the force. V is the velocity of that charge. So if the velocity were 0, it wouldn't matter what the rest of this stuff was because we'd still get 0. And we're multiplying times B, where B is the magnetic field. So every time you see a B, think magnetic field. Why B? Well, because M was used for different stuff. So one of the things that's kind of tricky about magnetic fields has to do with the nature of these force laws. Back when we did electric fields, you'll notice the Coulomb force law says the force is going to equal whatever Q is times E. Now, Q is a scalar, just a number, but E is a vector. And we know from last semester what happens when I multiply a scalar times a vector. It causes that vector to stretch or compress, but doesn't change the direction at all. And that means that in the case of the Coulomb force law, the force felt by a positive charge is going to be the same direction as E, right? Because if Q is positive, I multiply by E, the vector I get for F will point the same direction, but it might be longer or shorter. So with electric fields, the force that you get is always the same direction as your electric field. Your electric field points to the right, your force points to the right. The only exception to that is if I have a negative charge, put a minus sign here, this is going to flip and the force will be the opposite direction. But either way, if my electric field is to the right, that means that I'm having a force to the right or maybe to the left, but I'm never going to have one in some other weird direction. This, though, you'll notice that to get the force here, I've got to multiply a velocity vector times a magnetic field vector. And that means that I have to remember how to multiply two vectors and get another vector. That's what the x represents, is when I'm multiplying two vectors and getting a third vector as my product. It's called a cross product, and we've seen it before. We saw it back in chapter 10, actually 9, chapter 9 last semester. So I'm going to pull this aside for a second and remind you how cross products work. So if I've got vector A crossed with vector B, and that equals some new vector, vector C, the thing that you have to remember about those cross products is that the product is always perpendicular to both of the original vectors. Right. That's true of cross products in general. Anytime you multiply two vectors together to get a third vector, that third vector is perpendicular to both A and B at the same time. Now, in our specific case today, that means that the force that we're going to generate is going to be perpendicular to the magnetic field. Unlike the electric field, which is the same direction as the force, the magnetic field is always perpendicular to the force. Period. End of story. So if you see B is to the right, you know for sure the force felt is never going to be to the right. It cannot be. So that's the first thing we have to remember. We also have to remember that if I wanted to find the magnitude of that third vector, we would take the magnitude of A times the magnitude of B times the sine of the angle between A and B. So what's going to happen is if vector A points to the right and vector B points downward, the angle between them is 90, and the sine of 90 is 1. So multiplying these two vectors together, I would have something non-zero, whatever A was. Let's say that's 5 units. Let's say that this is 6 units. So 5 times 6 is 30, times the sine of 90, which is 1. So in this case, A cross B would have a magnitude of 30 units. But what direction would it point? Because it's got to be a vector. And we had to learn what direction that was. There's a rule for that. It's called the right-hand rule. And the way you implemented the right-hand rule was you took your right hand and you would take the fingers of your right hand and point them in the direction of whichever vector was listed first. Notice I'm doing A cross B, not B cross A. So in this case, vector A points this direction. So I'm starting with my fingers pointing in that direction. However, I'm going to have to bend my fingers in the direction of the second vector. So without taking my fingers out of that direction, I want to bend my fingers towards the bottom of the page. But the way I'm holding my hand right now, I can't do that. My fingers don't bend that direction. So what I've got to do is rotate my hand. My fingers are still pointing in the required direction. And now I'm going to bend my fingers, not my wrist, towards B. Now, when I do that, my thumb is pointing into the page, which tells me that A cross B is 30 units into the page. And again, the way we denote a vector that's into the page is imagine an arrow flying away from your face. You would draw little tail feathers at the back end of the arrow going away from you. So that means into the page. By contrast, had I done A cross B like so, well, now my fingers have to point to the right, or actually to the left, excuse me. Right? Then I would when I do the right-hand rule, my thumb points towards the camera, which is out of the page. So these are both still 5 and 6. That'd be 30 units out of the page. So those are all tricks we learned back in chapter 9 and 10 last semester, but it's going to be particularly important now. What helped us last semester was that when we were dealing with torque, you kind of knew sort of how torque worked because you've seen things twist and turn and rotate in real life. But with magnetic fields, you haven't seen any of that stuff, right? You don't have a lot of experience dealing with it. Note that sine of theta means that if I took vector A, thanks Max, shut up, and vector B, and they were both pointing the same direction, well, what would happen is the angle between them would be 0 degrees, and the sine of 0 is 0. So here, A cross B would equal 0. And of course, who cares what a direction a 0 vector is? So that little aside is going to help us because it means that magnetic fields will always generate a force perpendicular to the magnetic field and also perpendicular to the velocity at all times. That's going to make life interesting, to say the least. Notice if V and B are in the same direction, no force. So if there's a magnetic field pointing to the right and I have a particle that's charged traveling to the right, it won't feel any force from that magnetic field. It's going to matter what direction that charge is traveling, and to the extent that that force is perpendicular, or that velocity is perpendicular to the magnetic field, it will generate a force. But if it's parallel, I get nothing. So far, that's a really huge difference. We also had a difference in terms of how we visualize the fields. We learned how to draw electric field lines back in chapter 18. And what's going to happen is if I had a single positive point charge, the field lines would emanate away in every direction, right? That's what the electric field lines look like for a point charge. And notice that meant in particular that lines began on positive charge or they would end on negative charge. Right. That's true for electric field lines. But for magnetic field lines, that's not what they're going to look like at all. For a magnetic field line, if I have a positive point charge and it's traveling, say, to the right, then what's going to happen is it's going to generate magnetic field lines that don't emanate away from the charge, but instead swirl around it. So magnetic field lines form closed loops. Closed loops don't have a beginning or an end. And that's very, very different from what we see with with electric fields. Magnetic fields don't begin or end, they just form loops. Now, how would I determine how much of a magnetic field I have? Well, for point charges anyway, we have a formula. For the electric field of a point charge, we just took the definition of the Coulomb force law, worked it over, and found that for an electric field, the magnitude of that electric field was kq over r squared. And of course, it always points radially away, so that was the direction. So this is how we found the electric field of a single point charge. The magnetic field of a point charge is a bit more complicated. It follows something called the Biot-Savart law. And it says that your magnetic field stop it. So this is the bios of our law. And if I wanted to guess to complete the symmetry, I drew this as a magnitude. If I wanted to do this as a vector equation, I could do it a little differently. I'll come back to that in a minute. So let's break this bios of our law down, and we'll see that it's not as complicated as it might look. It looks kind of ugly, but really it's not. So I've got a point charge who's creating a magnetic field. All this stuff right here, this is just a bunch of constants. This is like the magnetic version of the Coulomb constant K. Now, this mu naught is called the permeability of free space. But almost nobody ever actually uses that name. They just call it mu naught. It's a holdover from an older theory that's long since been discarded, but the name had kind of stuck. And it's got a number. The value is 4 pi times 10 to the negative 7th Tesla meters per amp. Just a number. And you'll notice mu naught's going to show up in a lot of equations in this chapter. But here it's mu naught over 4 pi, and mu naught is 4 pi times 10 to the minus 7. So this entire leading factor is just 1 times 10 to the minus 7. It's super easy to remember. Now, Q is obviously the charge who's creating the magnetic field. That's pretty obvious. V is the velocity that's creating the magnetic field. And just like over here, R is how far you are from the charge. It's a distance. And of course, it goes as R squared, suggesting that if you've got a point charge flying around, it's going to create a magnetic field, but the magnetic field gets weaker the further away from the charge is. Now, the part that's probably giving you guys fits right now is what the heck is this? This R hat. Well, if you remember last semester when we learned about vectors, we learned about unit vectors. And the ones we most frequently used were I hat, J hat, and K hat, right? The X, Y, Z unit vectors. They were special vectors that had a length of exactly 1 unit, and they were mostly used to mark a direction. And R hat's going to be the same kind of way. R hat is going to mark a direction. It's a direction that points from the charge to the location that we're observing. So technically, I could have written this in vector notation. I could have said that not just the magnitude, but the actual value itself would be this number times R hat. Because R hat, if I'm looking over here, R hat points in that direction. I'm looking over here, R hat points in that direction. It's radially away from the charge towards where we're looking. Now, for the Biot-Savart law, notice I'll take that R hat vector and cross it with the velocity vector to get the direction of my magnetic field. So I'm doing another cross product. So let's go with that. Imagine that I've got a positive point charge, and for simplicity's sake, let's have the velocity of that point charge be coming straight out of the page towards the camera. So here's my positive charge. It's got a velocity towards the camera. Remember, the dot means you're seeing the tip of the arrow coming at your face. And I want to think about the magnetic field created by that charge. So this is my charge. If I look at the magnetic field over here, R hat would point from the charge towards where I'm going. V points out towards the camera. So doing the right-hand rule, I take my fingers in the direction of V, so my fingers had to come straight out towards the camera. Whoa, extreme close up. Then I have to bend my fingers in the direction of R hat. And so when I do that and bend my fingers, my thumb points towards the top of the page. So the magnetic field created by that charge at that location would be straight up. Now, what's going to happen if I look above the charge some distance? Well, if I do that, r hat points from the charge towards the place I'm looking, so r hat points in that direction. V still points out of the page. So start my fingers in the direction of V, bend them that direction. My thumb will point to my left. So the magnetic field at that location looks like that. What if I look over here? Well, V still points up towards the camera, but now R points that direction. So V, bend my fingers towards R. When I do, my thumb points towards the bottom of the page. And let's complete the cycle. For this one here, V is still toward the top of the page, or actually out of the page, excuse me. R points towards the bottom of the page. Thumb. And as promised, those field lines are going to form closed loops. And that's what's going to happen. So there's my electric or my magnetic field lines swirling around that charge. And I got that by doing V cross R hat over and over and over again. So it's complicated, but it's not the end of the world. And what we'll be able to do is to take these concepts and kind of run with them. But it's going to be weird because of all those cross products. So, daggone it. So let's try this out. That's why. Let's do a problem and let's play around with magnetic fields. And for the most part, let's go with a uniform field. So let's have a magnetic field have be uniform. And let's have it pointing, let's have it pointing out of the page. And let's take a positively charged particle and let's give it a velocity to the right. And I want to know, how does that magnetic field affect the motion of that particle? Well, we're going to be applying the Coulomb force law. To that particle. And of course, when I do cross products, the magnitude of that force, the number part of that force, is going to be whatever Q is times whatever the velocity is. Let's give it a velocity of, let's say, 1,000 meters per second. And let's give it a charge of 50 microcoulombs. So F will be the magnitude of Q times the magnitude of V times the magnitude of R hat. But R hat is a unit vector, so by definition, it has a magnitude of 1. So Q times V times 1 times the sine of the angle. Oh, excuse me, idiot. It's times B, not R hat, stupid. I was like, where's my B? Oh my goodness, get more sleep, Tom. Q times V times B times the sine of theta. Let's say the magnetic field is 5 Tesla. The Tesla is going to be our SI unit of magnetic field. It has nothing to do with the car company. It's actually named after the same guy the car company is named after, who had nothing to do with the car company. Nikola Tesla, super cool guy, weird, like kind of the prototypical mad scientist. So if I wanted to find that force, I could find the magnitude of that force easily enough, because here the sine of theta is going to be 1 because V is to the right, B is pointing out of the page, so they're 90-degree angles. Sine of 90 is 1, so Q times V times B. But if I want to know the direction of the force, that's a little trickier, because V is to the right, B is out of the page. So when I do that, my thumb is pointing towards the bottom of the page. So what's going to happen is this guy's going to feel a force pulling it straight down. Now, what's going to happen if I have a velocity to the right and a force that is perpendicular to that? Well, we learned last semester that if your force is in the same direction as your velocity, you will speed up. If the force is in the opposite direction of your velocity, you will slow down. This is neither. So this object will neither speed up nor will it slow down. However, that force will cause the velocity to change. So what will happen is the velocity was to the right, but as a result of that downward force, it's going to bend the velocity a little bit downward. So sometime later, my particle will be over here somewhere, and its velocity will now be the same size as before, still 1,000, it never changes the speed, but a bit more downward. Now, problem. At this location, the force will be in a different direction, because now V cross, so V cross B diagonally this way. No, sorry, force. So what's happening is the force is still perpendicular to V. It's going to bend even more. And so what's going to happen is every time I redraw this, my velocity has just bent. And what's going to end up happening is, we've seen this before in chapter 6 last semester. If I have a force perpendicular to my velocity, I won't speed up or slow down, but I will turn and move in a circle. So particles that are moving in uniform magnetic fields are going to tend to move in circles. This kind of motion is called cyclotron motion. Now, what do I know about that circle? Well, what I can do is I can apply what we've learned back in chapter 6 of last semester about uniform circular motion and combine it with what we know about the magnetic field right here. Now, we know from last semester that F equals ma, so I can set this equal to ma. But we also know that if I'm moving in a circle, which I clearly appear to be, my acceleration is the centripetal acceleration, v squared over r. Again, this is from chapter 6. If I take this expression and plug it in there, I get q times v times b. That's going to equal mv squared divided by r. Notice the velocity of the particle appears on both sides of the equation. And if I rearrange this and solve for r, this right here is called the cyclotron radius. And you'll notice that this particle, in response to that magnetic field, is going to swirl around in a circle But the size of that circle is going to depend on the mass of my particle, the velocity of my particle. If it's traveling faster, the circle will be bigger. It also depends on the size of the magnetic field. If I make the magnetic field bigger, it makes the circle tighter because the forces are larger. And that's what will happen. It won't speed up. It won't slow down. It's feeling a force continuously, but all that force will do is swirl it around in a circle. Now, sometimes that particular rotational motion is significant. Something that we learned last semester. I'm going to rewrite this just so we can see it on this sheet. We learned last semester that if I'm traveling around a circle at a constant speed, which we appear to be, my velocity would be equal to the distance that I go around the circle, 2 pi r, the circumference, divided by the period of rotation. That's t is the time for one complete cycle. And if that's the case, if I plug this expression in here, you'll notice r now appears on both sides of the equation. So all I've done is, remember, this equals 1. I just simplified that down, move the t over, boom. That's a 2. It didn't look like a 2, but it's a 2. So this is called the cyclotron period. So what this tells me is that if I have a moving particle in a magnetic field, it's going to go around and it's going to take a certain amount of time to make every one complete lap. Right? That's the period, is the time it takes for one lap around the circle. And what's cool is that the time for one lap, notice the velocity is gone, right? It doesn't matter how fast you're traveling, it'll take the same amount of time to go all the way around. If you're traveling faster, you might think it'll go around in a shorter time, but it won't, because the faster moving particles are going to go around a bigger circle. And the increased distance will exactly cancel out the effect from having the increased speed. A slower speed means you'd go around a smaller circle. So even though they're traveling slower, it'll take them the same time because they're not going around as far. Pretty cool. Now, of course, we also know from last semester that for periodic stuff, the frequency is 1 over the period. If the frequency, or if the period is the time for one loop, the frequency is the number of loops per amount of time, per second. So if I flip this, that's called the cyclotron frequency. And again, why do I care about any of this stuff? Well, if you've done any kind of NMR, what you're relying on is the precessional motion of charges in whatever your sample is. And so what an NMR is doing is it's looking at the frequency with which things oscillate in a magnetic field. You turn on a big magnetic field and watch what happens. And the frequency you get is going to depend on the charge of whatever it is you're looking at. So if I have a singly charged molecule, it's going to rotate with a different frequency than a doubly charged molecule. If I'm looking at an ion that's got a certain number of electrons, the frequency with those electrons are going to buzz around with in that magnetic field will depend on how much charge I've got. So you can get a picture of what the charge distribution is in a sample by looking at the frequency response rates from different locations. And that's how nuclear magnetic resonance works. So if you've done any NMR, you're doing a more complicated version of this particular process. So far, hopefully so good. So what we've learned is how to break down the mechanics of a particular magnetic field. So cool story. In Switzerland, there is a device called the Large Hadron Collider. Now, the Large Hadron Collider it's a device that is devised so that we can study the conditions that existed in the primordial universe, mere milliseconds after the Big Bang. And of course, in that time, all the energy of the entire universe was concentrated into a tiny little area. And what it means is that matter has access to way more energy during that period than it does today. And it allows matter to configure itself in high energy configurations that probably don't exist very often anymore. So we're kind of recreating the conditions of the early universe to try to see what things were like back at that time. The way we pull this off is we take protons, little charged particles, and we rev them up to ridiculously high speeds. Now, when I say ridiculously high speeds, I mean, like 99.9% of the speed of light, which is pretty doggone fast. And we rev them around in a big circle using cyclotron motion. Now, if we wanted to approximate what kind of magnetic field is required there, well, we know a couple things. We know that the Large Hadron Collider is a very big underground tunnel, and the tunnel goes in a loop 10 kilometers in diameter. So imagine I've got this big underground track that I'm sending my protons in. And that's a 10-kilometer diameter. Now, let's imagine that my particle is a proton. So if it's a proton, I know the charge. (1.6 times 10 to the negative 19th coulombs). I know the mass of a proton is about 1.67 times 10 to the negative 24th kilograms. And I want to rev this thing up to about, let's say, 90% of the speed of light. So that's about 2.7 times 10 to the 8th meters per second, which is blazing fast. Now, in case any of you guys are familiar with the theory of relativity, I will put this disclaimer out that I'm not paying any attention to relativistic effects here. That would make it more complicated. We're going to go simple here. But it turns out this mass is not the same at that speed as it is at low speeds, but we're going to ignore that for the moment. So the question then becomes, how much of a magnetic field am I going to have to generate in order to keep this particle traveling inside this little track? Well, we know that, again, the force is QVB. If I keep the magnetic field perpendicular to V, the sine of theta is going to turn into 1, which we can pull that off. We're going in a circle, so I can replace F with mv squared over r. right? Again, the V's cancel. And I'm solving for B this time. So the magnetic field I require is going to be M times V over Q times R. So M was 1.67 times 10 to the negative 24th. My velocity, meanwhile, 2.7 times 10 to the 8th. My Q is very tiny, 1.6 times 10 to the negative 19. And R is a whopping huge 10 kilometers or 10,000, excuse me, that's D, 5,000. I got to cut it in half, meters. So if I crunch those numbers, it turns out that at that speed, it's only going to take me about 0.56 Tesla. Now, is that a lot? We should probably get a sense of what the size of a Tesla is. Now, when you guys think of magnetic fields, you almost certainly think about the things that stick to your fridge. Now, the things that stick to your fridge, they're going to have a magnetic field of probably a few hundredths of a Tesla. That's about typical. If you've got one of those neodymium magnets, the really strong magnets, some of those you might get up to maybe half a Tesla, but that's pretty extreme. The biggest magnetic fields that I have ever seen personally are certainly bigger than this. We had my lab at Clemson. We had a couple of big high field magnets. The one that I used the most would go up to about 5 Tesla. But in order to pull off 5 Tesla, what we had to do was we had to get a big, about 75 kilograms coil, wrap the thing with several hundred turns of wire and send 100 amps of current through it, which is a lot of current. Put that through a regular coil of that size, and the coil would get so hot it would be a problem. So it had to be made out of superconducting wire. But in order to make that wire superconduct, we had to keep that superconducting wire in basically a large thermos filled with liquid helium at 4 Kelvin. So yeah, that was a lot. We had another magnet in our lab that could go up to, I think it's 10 or 12 Tesla, but that was even more extreme. So getting more than about 10 Tesla is pretty rough. There are experiments that they do in Nevada every year where they generate magnetic fields of several hundred Tesla. But in order to pull this off, here's what they've got to go through. So they have this big cave underground in Nevada, and they set up their experiments every year. And when it's time to do those experiments, and they'll have lots of labs will have their stuff set up there. It's not just one person. It's like lots of people collectively doing this. They'll generate a magnetic field as big as they can manage, and then what they do is they collapse the cave. Like the cave collapses in on itself. And what that does is it takes the magnetic field lines that are maybe this size, and it concentrates them together super tightly while the cave is collapsing. And for only a few milliseconds, you'll get magnetic fields of several hundred Tesla. But of course, then everything falls apart, your stuff gets destroyed, you rebuild the cave and do it again next year. So the point of this is that magnetic fields don't often get higher than a Tesla or two. And even then, it's only with great effort. If you're solving a problem and you get like 5 million Tesla, you're probably doing it wrong, because 5 million Tesla is a hugely large number. So get used to small values. This is not unusual. This is actually a pretty large magnetic field. It's probably about 50 times stronger than any magnetic field you've ever seen in your life. So that's pretty hefty. And they could certainly go higher than this, but maintaining this many Tesla all the way around this huge layer requires colossal amounts of cryogens. It's a pretty tough technical challenge. So, and of course, this is even only at 90% of the speed of light. It gets worse when you crank the speed up even more. So they're probably going to have to go to probably about 5 or 10 Tesla at
Question.
all around that thing. Yeah, Terry, what's up?
Hey, so I see you have 5,000 in a denominator for the R.
Yeah.
How did you get that? Because I see that the diameter is 10. Like, did you convert something?
Well, 10 kilometers, kilo means 1,000.
Oh, okay. I didn't. All right. I see.
Yeah, so yeah, 10 times 1,000 is 10,000, but then I had to cut 10,000 in half, became 5,000.
Okay. So you converted
Yeah.
it to meter.
Yes. Always. I'm in the habit usually of, when I see a unit that's not in SI units, I almost always out of habit will convert those non-SI units into SI units. And the reason is because I know that if I put SI units in, I will always get SI units out. So I know if I'm doing this expression here, and I put kilograms in for my mass, meters per second in for my velocity, coulombs in for my charge, and meters in for R, the unit that's going to come out is going to be Teslas.
Okay.
If I put some other weird unit over here, I get some other weird unit for B, and I don't want to do that. I don't want to have to think about what that is. So it just makes my life easier 9 times out of 10 to use SI units. So reflexively, when I see that, I'm like, oh, that's 10,000. So get into that habit. It will help you tremendously. So that's sort of an introduction to magnetic fields and cyclotron motion. So far, so good. You guys feel pretty solid about that?
Yes, sir.
I dig it. So what will happen is when you go to actually generate a magnetic field, we know how to find the force from a magnetic field, but what we don't know how to do is to figure out how they're generated. We'll deal with that probably tomorrow. However, even here, we run into some issues. And one of the issues is, actually, let's table that discussion. Let's do that tomorrow as well. Let's do one more example of cyclotron motion real quick. Let's talk about mass spectrometers. Now, many of you guys have used mass spectrometers before in your lives. What's a mass spectrometer?
A mass spectrometer, it reads out the like, what is it called? It's like, because I used this in research before.
Yeah.
It details like the certain peaks that are in a liquid,
Or usually a gas, but sometimes.
Yeah.
So yeah, I guess you could do. I don't know. So yeah, what would happen is your mass spectrometer, usually your output is going to be like some kind of graph, right? And what this would be is like the mass of the particles, and then this right here is like the number, or the basically it scales to the amount of stuff. And so you'll get like right? And so what's going to happen is, if you got some gas that's a mixture of a whole bunch of different kinds of molecules, what's going to happen is you'd be like, oh, this peak right here means I've got a whole bunch of stuff that has this mass. And this peak right here says I got a whole bunch of stuff that's this mass. And a whole bunch of this stuff that's this mass. And so you can figure out the constituents of some gas of unknown particles by looking at the response on that mass spectrometer. Pretty cool. Now, I didn't realize this until I was an adult, but my grandfather, we lived in West Texas growing up, and my grandfather's job was working on mass spectrometers, little portable mass spectrometers that they would deploy out in the oil fields of West Texas. And the idea was that, people would go out, they drive out in the middle of nowhere where they think there's going to be some oil. They drill a test hole, and then they sample some of the gases that vent out of that test hole. And the idea was, if they had the right mix of certain kinds of petrochemicals in that test hole, that suggested that there was probably oil down there. And if you didn't have certain things in certain abundances, they're like, it's probably not worth wasting our time dropping a drill here to do more drilling, because nothing much is down there. So being able to have this portable device that could tell you on the spot how much of each kind of stuff is there was super important. Now, we know enough physics to understand how a mass spectrometer works. It's super easy. And since you guys have frequently used them, I usually want, before I move on to other stuff, I usually like to take some time to talk about how a mass spectrometer works, because it's kind of cool. So let's do that before I move on. So here's what's going to happen in any mass spectrometer. And there's different varieties. So we'll be making some generalizations in places. But you're always going to start off with a sample of gas, right? Now, in that gas, you've got a whole bunch of different kinds of stuff that you don't know. Maybe it's the stuff coming out of that oil well, and maybe some of it is methane, some of it is octane, some of it is pentane, all kinds of weird, crazy organic molecules. And you want to know how much of each kind you've got so that you can figure out whether you've got oil. Now, the first thing I need to do is make sure that this gas is charged. So what you're going to do is you're going to send this gas through an ionizer. Now, there's different kinds of ionizers. Probably the most common one is called an electron impact mass spectrometer, where you literally send your gas and you bombard it with a beam of electrons. And so occasionally what's going to happen is those molecules will pick up an extra electron and now become singly ionized. And that causes all kinds of problems that if you take PChem, you'll learn about them. God help me, I don't care about them. But like if you hit a molecule with an extra electron, sometimes that will cause the molecule to fragment. So sometimes rather than getting a peak for your particular chemical, maybe you're going to get a peak for the two fragments, but you have to be able to figure out, oh, well, if hitting this molecule with electrons tends to make it split into these kinds of fragments. So seeing these abundances of those fragments tells me I really had this other original chemical. It's a whole science to that, which if you take more spectroscopy, you'll have to familiarize yourself with, but that's beyond the scope of this class. So anyway, we're going to hit this gas with this ionizer, and what's going to come out is now ionized gas. Now, the problem is the particles in that ionized gas, they're flinging around with all kinds of random velocities. So what we're going to do is we're going to send this through a velocity selector. All right. And here's how the velocity selector works. Inside that velocity selector, we've got the gas coming in right here. And the escape for the gas is right on the other side of the velocity selector. So you have this little chamber that your ionized gas can go through. And inside that chamber, we're going to apply two fields. One of those fields is going to be an electric field, and the other field is going to be a magnetic field. So inside here, let's say that I've got an electric field and the electric field points straight down. Now, if I have negatively charged particles, let's say that they're negatively ionized, then what's going to happen is the force from the electric field is going to be the opposite direction. So I would get a force from the electric field that is upward. I'm using red for the electric field. And so what's going to happen is that would tend to make my electron or my charged particles deflect upward, but that means they're not going to make it out the gap, right? In order for them to make it out the other gap, they've got to go straight across undeflected. Now, in that same gap, I'm going to, in addition to the electric field, turn on a magnetic field. But what I want is I want for the magnetic field to generate a force in the opposite direction. The idea is that the force from the electric field and the force from the magnetic field, if they're in opposite directions, they might cancel out. And if they cancel out, I'll have particles travel undeflected and make it out the other side of the velocity selector. Now, if I want the force from the magnetic field to be downward, what direction does my magnetic field have to point? Well, the velocity is going to be at least a little bit to the right. So if I do V cross B, if B is into the board, that's the wrong direction. That's up. I need it to be downward. So that means the magnetic field has to point out of the board. So it'll be perpendicular to E. However, that'll cause a force that's downward. And now what's going to happen is, if I think about this, the force felt by the magnetic field will be Q times V times B. The force due to the electric field is going to be Q times E. So since they're in opposite directions, I can say that Q times E minus Q times V times B equals MA, right? F equals MA. Except I'm particularly interested in the charges that are going to make it all the way through the selector and not get deflected up, not get deflected down. They're going to go straight across. That's going to happen when these two forces cancel out and the acceleration equals 0. But that means I need QE to equal QVV. And you'll notice that when I do that, the Q's cancel. And if I solve this for B, I find that V is going to equal E divided by B. So what's going to happen is, by tuning what E and B are, I can choose to have particles come out of that selector and all of them will have the same velocity. And that's awesome. You've got this gas of random particles, all of them traveling every which way, but the only ones who make it out of this little gap are the ones that have this particular velocity. So now I've got a single speed of gas particles, all of them ionized, heading into the actual spectrometer. Now, what's going to happen inside that spectrometer is I'm not going to have an electric field. I'm only going to have a magnetic field. So inside there, I'm going to have the same magnetic field that we had inside the velocity selector. But that means that all these particles are going to feel a force downward. And how much force are they going to feel? Well, QVB. But now, since they don't have the electric field canceling it out, they go through cyclotron motion, and they will travel I can't do it. MV squared over R. And so what's going to happen is they will travel with a cyclotron radius. And if you look inside that spectrometer, what's going to happen is, here's my particles. They're coming in from my velocity selector. And they're going to travel in a circle, but the radius of that circle depends on the mass of my particle. Remember, they all got the same V, they all got the same Q, they all got the same B, but the ones with the most mass are going to have the biggest R's. So the small mass particles are going to go dee, 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 in tiny little circles. The big mass particles are going to go dee, 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 dee. They make that noise. I'm serious. And so the larger the mass of the particle, the larger the radius that it travels in. And so what you do in a mass spec is you've got little detectors, and you put those detectors at varying distances from your entrance. And what you measure at each of those detectors is you're measuring the current, because you got a certain amount of charge hitting that spot. If you measure how much charge per time, that's going to tell you how many particles you've got. So more current means more particles. And that's what these peaks are doing. These peaks are just counting how many times that particular detector got hit. And that allows you to know how many particles of how many different bits of mass you've got. So it's a super simple, but really kind of elegant way of discriminating between what's inside that material. And it's certainly one that you guys will, if you haven't already, have a chance to play around with here in the department. So pretty cool to understand how that works. And at the end of the day, it's just utilizing the velocity dependence of the Lorentz force by making that force depend on the velocity, because inside that velocity selector, QE is a constant. All those particles feel the same force, but the faster they're going, the more magnetic force you feel. And so only the ones whose magnetic force cancels out the Coulomb force make it into your selector. And then the cyclotron motion allows each particle with different mass to land in different places. Pretty cool. All right. So in terms of the mechanics of the Coulomb force law, you guys are pretty well situated. I'm going to go ahead and table the rest of this. We'll come back tomorrow and we'll learn, how do I know how much magnetic field I've got? We've seen the Biot-Savart law, which only works for point charges, but more often than not, we're not going to be dealing with just point charges. We're also going to deal with the fact that in the real world, we often aren't just looking at the velocities of charged particles, we're looking at currents. So tomorrow we'll learn how to deal with the magnetic forces created by or felt by currents, because currents are the things that we typically measure in the laboratory. Are there any questions before I let you guys go?
No, sir.
All right. Have a good one. Remember to take your exam sometime in the next 2 days, and I'll talk to you later.